Welcome back everybody. Before we start coding, let me quickly show you what we have built so far. We now have our own custom task manager called Process Master 2026. We can load running processes, search and filter them, display detailed information, open the file location of an application, and even terminate running processes directly from our own tool. Not bad at all for just a few videos. Now, if you haven't watched the previous part yet, I highly recommend doing that first because that's where we built the complete process page and integrated it into our application. And if you're completely new to this project, don't worry. You can also start from the beginning of this mini-series where we cover the basics of the process class and learn how to communicate with running applications using C# and Win forms. Today we're taking this project to the next level. Because a real task manager doesn't just show processes. It also shows what's happening inside your system right now. How much CPU is being used? How much memory is being consumed? How many processes are currently running? And most importantly, it visualizes all that information with live graphs. So that's exactly what we're going to build in this video. By the end of this tutorial, our task manager will feature a fully working performance page with real-time CPU monitoring, RAM monitoring, process statistics, and beautiful live graphs that update automatically. This is where our little project starts to feel like a real professional system tool. So open Visual Studio, grab something to drink, and let's build something great. First we open the project from the previous part where we already created the foundation of our task manager. If you haven't completed the last video yet, I highly recommend finishing that one first because that's where we built the process page and integrated it into our main application. Now it's time to create the second major page of our task manager. The performance page. This page will eventually show live CPU usage, RAM usage, running processes, and real-time graphs just like the Performance tab in the Windows Task Manager. So let's start by creating a new class called Performance Page. Since this page will be displayed inside our main application, we inherit from user control. Now before we start building the UI, we need to declare all the variables that our page will need. First, we create 3 panels. One for CPU information, one for RAM information, and one for process statistics. Inside those panels, we will later display graphs that update in real time. That's why we also create 3 graph panels. One for the CPU graph, one for the RAM graph, and one for the process count graph. Next, we create 3 labels. These labels will display the current values, such as CPU percentage, RAM usage, and the number of running processes. To keep everything updating automatically, we also create a timer. This timer will run in the background and refresh our data every second. Now we need access to real system information. For that, we create 2 performance counters. One for CPU usage and one for available memory. We also create a computer info object which allows us to access additional system information, such as the total amount of installed RAM. And finally, we create 3 lists. These lists will store historical values over time. One list for CPU data, one list for RAM data, and one list for process counts. Later, these values will be used to draw our live graphs. At the moment, we are simply preparing everything we need. Think of this step as building the foundation before we start constructing the actual performance page. Once all these variables are in place, we can move on and start bringing the page to life. Now let's look at the constructor of our performance page. This is the code that runs automatically when the page is created. The first thing we do is set the docking style to fill. This makes sure our page automatically takes up all available space inside the main application window. After that, we set the background color. We're using a dark color here because we want our task manager to have a modern professional look, similar to many system monitoring tools. Next, we create a new instance of computer info. This object gives us access to important system information, such as the total amount of installed memory. Now that our basic setup is complete, we start calling our helper methods. First, we call init counters. This is where we will prepare the performance counters that allow us to read live CPU and RAM information from Windows. After that, we call build UI. This method will create all the controls, panels, labels, and graph areas that make up our performance page. And finally, we call start timer. This starts the timer that will continuously update our data and graphs in real time. In short, this constructor prepares the page, loads the system monitoring components, builds the user interface, and starts the live updates that will power our performance dashboard. Now let's look at this method. This method is responsible for setting up the performance counters that we will use throughout our performance page. Performance counters allow us to read live information directly from Windows. The first counter we create is for the CPU. Here we tell Windows that we want to monitor the total processor usage across all CPU cores. This means we can later ask Windows how busy the processor currently is and get a percentage value back. Next, we create a memory counter. This counter gives us the amount of available memory in megabytes. Using this information together with the total installed memory, we can calculate how much RAM is currently being used. And finally, we call CPU counter. Next value once. This might look a little strange, but it is actually very important. The CPU counter needs an initial reading before it can return accurate values. So we call it once during setup and then use it later when our timer starts updating the data. In short, this method prepares the connection to Windows performance monitoring so we can read live CPU and RAM information for our performance page. In this part we are building the main structure of our user interface, and everything here is focused on organizing the dashboard panels and connecting them to their live data visuals. First, we start by creating three main UI sections. One for CPU usage, one for RAM usage, and one for running processes. Each of these panels is created using the same helper method called createPanel. This keeps the design consistent and avoids repeating layout code. At the same time, we are also getting back two important things from each call. We receive a label reference that will later show the live value, and we also receive a graph panel where we will draw the performance history. So after this step, we now have three fully prepared UI blocks. One for CPU, one for memory, and one for processes, each already connected with their display elements. Next, we add all of these panels into the main form. This is done through the controls collection. By adding them here, we make them visible on the screen and part of the layout hierarchy of the application. Without this step, the panels would exist in memory but would never appear in the user interface. After the UI elements are placed, we move into the visual behavior of the graphs. Each graph panel gets a paint event assigned. This is where the real-time drawing happens. For the CPU graph, we attach the draw CPU method. For the RAM graph, we attach draw RAM. And for the process graph, we attach draw proc. This means every time one of these panels needs to be redrawn, Windows will automatically call the correct drawing method. This is what allows the graphs to update dynamically and reflect live system performance. So overall, this section is responsible for three things. It creates the UI structure, it attaches everything to the form, and it connects each graph to its drawing logic so the dashboard becomes fully interactive and live updating. In this part we are setting up a very important concept that helps us control what kind of graph we are drawing, and how we keep our drawing logic clean and reusable. We start with a simple enum called graph type. An enum is basically a named list of fixed values. Instead of using random strings or numbers in our code, we define clear labels. In this case, we define three types: CPU, RAM, and processes. This makes the code much safer and easier to understand because we always know exactly what type of graph we are working with. So now instead of guessing what a value means, we can directly say, this is a CPU graph, this is a RAM graph, or this is a process graph. Next, we move into the drawing methods. We have three separate paint handlers, one for processes, one for RAM, and one for CPU. Each of these methods is extremely small and clean because they all follow the same pattern. They don't contain full drawing logic themselves. Instead, they simply forward the work to a shared method called drawGraph. For example, when the process graph needs to be drawn, the drawProc method is triggered. It takes the graphics context from Windows and then passes it into drawGraph along with the process history data, the graph panel reference, and the graph type. Process value. This tells the system exactly what kind of graph it is dealing with. The same pattern is used for RAM and CPU. The drawRAM method sends RAM history data and marks it as graph type. RAM. The drawCPU method sends CPU history data and marks it as graph type. CPU. So what we achieved here is a clean separation of concerns. Instead of writing three different complex drawing functions, we now have one central drawing engine that handles everything, and these small methods only decide what data and graph type should be used. This makes the system much easier to maintain, because if we ever want to change how graphs are drawn, we only need to modify one method instead of three. In this part we are building the core engine of our performance graphs, and this is where everything comes together visually. We start with a single method called drawGraph. This is the universal drawing system that handles CPU, RAM, and process graphs all at once. Instead of writing separate drawing logic for each one, we use one shared function that takes in four important inputs. We receive the graphics object, which is the canvas we draw on. We get the data list, which contains the historical values. We also get the panel area, which defines where the graph should be drawn. And finally, we get the graph type, which tells us what kind of data we are working with. The first thing we do is a safety check. If we don't have at least 2 data points, we simply return. Because without enough data, we cannot draw a meaningful line graph. Then we enable anti-aliasing. This makes the graph line smooth and visually clean instead of pixelated or jagged. Next, we define the drawing area. We set a margin so the graph doesn't touch the edges, and then we calculate the usable width and height inside the panel. This ensures everything stays nicely aligned inside the UI. After that, we create 2 pens. One for the grid lines and one for the actual graph line. The grid is drawn in a subtle transparent white so it doesn't distract the user. The main graph line is drawn in a strong color so it stands out clearly. Now we need to scale the graph correctly. For that, we call getMax based on the graph type. This is very important because each metric has a different range. CPU always goes from 0 to 100%. RAM depends on the total physical memory of the system. And processes use a fixed upper limit to keep the graph stable. For CPU, we return 100 because it is always a percentage. For RAM, we calculate the total physical memory of the system so the graph matches real usage. And for processes, we use a fixed value like 500 to keep the visualization stable even if the number of processes fluctuates. Then we draw the background grid. We divide the height into 5 equal sections and draw horizontal lines. This gives us a visual reference so we can easily read values on the graph. After that, we move to the actual data plotting. We only take the last 60 values to keep the graph responsive and clean. Then we loop through the data and connect each point with a line. For every step, we take 2 consecutive values. We calculate their x positions based on their index, spreading them evenly across the width. Then we calculate their y positions by converting the raw values into screen coordinates using the max value scaling. This is what transforms raw numbers into a proper visual graph. Once we have both points, we draw a line between them. This repeated connection of points creates the smooth real-time chart effect that updates over time. Finally, we draw a border rectangle around the entire graph area. This gives it a clean frame and visually separates it from the rest of the UI. So overall, this section is the heart of the entire dashboard. It takes raw system data, converts it into visual coordinates, and renders a smooth, real-time performance graph that updates dynamically for CPU, RAM, and process monitoring. In this part we are setting up the heartbeat of our entire application, and this is what makes the dashboard feel alive and constantly updating. We initialize a new timer object. This timer is responsible for triggering updates at a fixed interval, so we don't have to manually refresh the UI. Next, we define the interval. We set it to 1000 milliseconds, which is exactly 1 second. This means every second, the timer will automatically trigger an event. This is the perfect balance for a performance monitor because it gives us real-time updates without overloading the system. After that, we connect the timer to our update method. This is done through the tick event. Every time the timer reaches its interval, it fires this tick event, and our update method gets called automatically. This is where we will refresh CPU usage, RAM values, and process data. Finally, we start the timer. From this moment on, it runs continuously in the background and keeps triggering updates every second. So in simple terms, this small section is what transforms the application from a static UI into a live monitoring system. It acts like the engine that keeps everything running and ensures all graphs and values stay constantly up to date. First, we read the current CPU usage. We do this using the performance counter, and next value gives us the latest CPU percentage at that exact moment. This value is constantly changing, so this is what gives us real-time CPU monitoring. Next, we move into RAM calculation. We first calculate the total physical memory of the system and convert it into megabytes so it is easier to display. Then we read the available free memory using the RAM counter. After that, we calculate used memory by subtracting free RAM from total RAM. This gives us a clear picture of how much memory is actually being used. Then we calculate the number of running processes. We simply get all active processes from the system and count them. This gives us a live process load indicator. After collecting all three values, we push them into our history lists. We use the add method to store CPU, RAM, and process values over time. This is what allows us to build the graph history instead of just showing a single snapshot. Then we update the UI labels. The CPU value is shown as a percentage. The RAM value is displayed in a used versus total format so the user can clearly see memory consumption. And the process value is shown as a simple number. Finally, we refresh the graphs. We call invalidate on each graph panel. This forces Windows to repaint the panels, which triggers our draw graph method again. That is what makes the graphs update visually in real time. So overall, this method is the brain of the system. It collects live system data, processes it, stores it for history, updates the UI text, and finally refreshes the graph so everything stays synchronized and continuously updating every second. We start with a simple helper method called add. This method takes two inputs. First, a list of floating point values, which represents our historical data. And second, a new value that we want to insert into that history. The first thing we do is very straightforward. We add the new value to the list. This is how we continuously build up the live data stream for CPU, RAM, or processes over time. But if we stopped here, the list would grow forever. That would eventually slow down the application and create unnecessary memory usage. So we need a limitation system. That's why we add a simple condition right after. We check if the list has more than 60 entries. If it does, we remove the oldest value, which is always at index 0. This creates a sliding window effect. Instead of storing all historical data, we only keep the most recent 60 samples. This is exactly what we need for a real-time graph, because we only care about the latest performance trends, not everything from the start of the program. So in simple terms, this method acts like a buffer manager. It continuously feeds new data into the graph system while making sure memory usage stays stable and performance remains smooth. This small piece of logic is what keeps the entire dashboard fast, efficient, and perfectly optimized for real-time updates. We start with a method called createPanel. This method is responsible for generating one complete performance block, including the header section, the value display, and the graph area. The method takes three important inputs. First, we receive a title, which defines what the panel represents, like CPU usage, RAM usage, or processes. Second, we pass a reference to a label, which we will later use to update the live value from outside the method. And third, we return a graph area through an output parameter, which will be used for drawing the live graph. Inside the method, we start by creating the root panel. This is the main container for the entire UI block. We dock it to the top so that all panels stack vertically. We also set a fixed height to keep the layout consistent. Then we apply a dark background color to match the modern dashboard style. Next, we create a header panel. This is the top section of the UI block where the title and live value will be displayed. We also dock it to the top and give it a smaller height so it sits neatly above the graph area. The same dark theme color is applied so everything feels unified. Now we create the title label. This label simply displays the name of the metric. We set its text, make it white for contrast, apply a bold Sego UI font, and position it on the left side of the header. This gives the panel a clear identity. After that, we create the value label. This is the most important dynamic element in the header. It starts with a default value of 0, and we style it with a bright blue color so it stands out visually. This label will later be updated in real time to show CPU percentage, RAM usage, or process count. Both labels are then added into the header panel so they appear together in the top section. Next, we handle layout alignment. We attach a resize event to the header so that every time the panel changes size, we automatically reposition the value label to the far right. This keeps the UI clean and always properly aligned, even if the window size changes. After that, we assign the value label to the reference parameter. This is a key step because it allows the outside code to directly update this label later during runtime. Then we create the graph area panel. This is where all the live drawing happens. We dock it to fill the remaining space inside the root panel and apply a slightly darker background so the graph stands out clearly from the header. We also enable double buffering for the graph area. This is very important because it prevents flickering when the graph is constantly redrawn every second. It makes the animation smooth and professional. Now we assemble everything. We first add the graph area to the root panel, and then we add the header on top. This order ensures the layout is correct and the header stays above the graph. Finally, we return the root panel, which now contains a fully built, reusable dashboard component. So overall, this method is a UI generator. It builds a complete performance panel from scratch, connects the live value label for external updates, prepares a smooth graph area, and ensures everything is perfectly aligned and reusable across CPU, RAM, and process sections. Normally in WinForms, when a control repaints very frequently, you can see flickering or visual tearing. This happens because the screen is being drawn directly frame by frame. To fix that, we use a technique called double buffering. But in this case, the double buffered property is not publicly accessible for every control in a simple way. So instead of setting it directly, we use reflection to access it internally. We call invoke member on the control type, and we target the property named double buffered. We specify that we want to set a property, and that we are working with an instance level, non-public member. This allows us to bypass the normal access restrictions safely in this context. Then we pass the control we want to modify, and we set the value to true. This enables double buffering for that specific control. What this does in practice is very important. Instead of drawing directly onto the screen every time the graph updates, the system first draws everything off screen in a hidden buffer. Once the drawing is complete, it is displayed all at once. This removes flickering completely and creates a smooth, stable animation effect. So in simple terms, this small helper method is what makes our real-time graphs look clean, fluid, and professional, even though they are updating every single second. So now we are at the final step, and everything we built before is ready to be connected into our main application. At this point, the new page is already fully created and working on its own. So what we need to do now is integrate it into our main form so the user can actually access it from the interface. We start with the first step, which is creating the required variable for the new page. This is important because our main form needs to hold a reference to every page we want to display. Without this, we cannot switch between pages or manage them properly. After that, we move into the build UI method. This is where we update the sidebar navigation. Here we add a new button for the additional page. This button becomes the entry point for the user to open the new view. We also attach a click event to this button, so when it is pressed, the application knows exactly which page to load and display inside the content area. This is the core idea of our navigation system. Instead of opening new windows, we simply swap the content inside the same main container. That keeps the application fast, clean, and modern. Then we move to the load pages method. This is where all pages are initialized when the application starts. Here we create an instance of the new page and store it in our main form variable. This ensures the page is ready in memory before the user even clicks the button, which makes the switching instant and smooth. So now let's test the new page inside our application. Everything is already connected, the button is in place, the page is initialized, and the navigation system is working. So when we start the application and switch to the new page, we expect everything to load correctly. But right now, something doesn't look quite right. There seems to be an issue, and the interesting part is that the whole system is working. Except for one single value that is not behaving correctly. And this is exactly the kind of situation you will face in real development. Everything can look perfect on the structure level, but one small value mismatch can break the entire visual output or make it look wrong. So instead of rushing, we carefully inspect the UI behavior. We compare CPU, RAM, and process values. We check the labels, the graphs, and the update method. Everything else seems fine, but one value clearly stands out as incorrect. Now this is the challenge part. We need to think like a developer and not just look at the code, but also at the logic behind the data flow. Where is this value coming from, how is it calculated, and where is it displayed? Because most of the time, these bugs are not big problems. They are usually a small mismatch, like a wrong variable, a wrong assignment, or a small calculation issue. So take a moment, review it carefully, and try to find it yourself before we reveal the fix. In the next step, we will identify exactly which value is wrong and correct it so the performance page works perfectly as intended. Now this is a really important moment because we are dealing with a very subtle but critical bug inside our graph rendering logic. At first glance, everything looks completely correct. The graph is looping through the data, calculating points, and drawing lines. But there is one small issue in how we are accessing the second value of the line segment. The problem is in this line. We are currently using a fixed index for the second value instead of calculating it dynamically based on the loop position. That means every single line segment is trying to connect to the same data point instead of moving through the dataset step by step. So instead of the graph flowing naturally, you would either get a broken line, repeated values, or an incorrect visual pattern that does not represent real system history. And this is why this bug is so important to fix. Because in a real-time performance monitor, the graph is not just decoration. It is the core visual representation of your system data. If even one index is wrong, the entire meaning of the graph becomes misleading. The correct logic is that both values must move together through the dataset. The first value uses the current position, and the second value must use the next position in the sequence. That is what creates a proper line between two consecutive points. So the fix here is very simple, but extremely important. Instead of using a fixed index, we must make sure the second value follows the loop progression correctly. Once this is corrected, the graph will instantly become smooth, accurate, and fully aligned with the real CPU, RAM, and process history. This is a perfect example of how a single small indexing mistake can completely break visual data representation, and why careful attention to array access is critical in every real-time system. And that's the point where everything comes together. You've now seen how the performance page works, how the graphs are built, and how even a small bug can affect the whole system. This is exactly the kind of thinking you need when building real applications. Now I want to take this project one step further, but this is where you come in. What should we build next? A task manager extension, a system tray tool, a startup manager, or something completely different? Write it in the comments and I'll build the next page based on what you choose.